Good afternoon. This is my second talk related to plane graphs and not diagrams. So I will recall the topics of the previous talk shortly, but first let's start from history. I wrote here several names, some of them famous like Euler, some of them are not that well known like Kuhn. So let's tell you why I'm doing this. So last time I said that the first person, and I should say about knots, so here I have nice rope. So in knots it's important that we don't take exact position into account. The formation is okay as long as we don't cut and glue. So let's go to the history. So I was mentioning that it was Vandermonde, Alexandre Théophile, French mathematician Vandermonde, who was the first person who considered knots as part of mathematics. And Vandermonde was motivated by ideas of Leibniz. About Leibniz, probably you heard a lot, and probably know that he was one of the persons who created, together with Newton, calculus, but he has plenty of other ideas. And one of the ideas of Leibniz was that old geometry is not sufficient, that there is need for some new geometry, which is not taking into account only distances and measurements, but is flexible, like this knot is the same whether I rotate this or put in this position or this position in this position, only relative position of arcs is needed. So Leibniz suggested new type of geometry, and he called this geometry geometria situs, geometry of position. So Vandermonde was motivated by Leibniz, and he said knots should be studied mathematically, had in mind example of geometria situs. He said in knots or nets or braids, exact position is not important, only relative position, on the relative position of strings, but not exactly how they are positioned. So now let's go back with Leibniz. Leibniz was not the first person having such ideas, however he really presented them clearly and was very influential. Leibniz always stressed that when he was young, he was motivated by the work of Anastasius Kirchner. Anastasius Kirchner is not well known. He was a very interesting person, German Jesuit in Rome. He wrote a lot of volumes, sometimes very confusing, but always these volumes were nicely illustrated. And because of this, for example, father of Leibniz bought these volumes to his library. So maybe I should mention here that these volumes were very influential in science in Latin America. They were first mathematical works which Jesuits brought to Latin America, and people who could study them. So this was about Kirchner, but even before Kirchner, there was Ramon Llull, probably should be pronounced Spanish or Catalonian scientist, philosopher, and he has idea of combinatorial machines. And these combinatorial machines were later considered by Kirchner, and Leibniz was very much interested in combinatorial machines, and he always stressed that Dewey's work was influential. In modern times now we know we are discovering work of Dewey about voting, for example. But for combinatorics, later graph theory, knot theory, he's really the earliest precursor, we can say. So this is about Leibniz and Vandermonde. Then, what was the first convincing example of geometria situs? It was, and I mentioned this already in previous talks, it was Euler's problem of bridges of Königsberg. And here I could stop a little. So Euler wrote a very influential paper. Everybody later was citing bridges of Königsberg, etc. So it is more or less 1735, 36. I will explain this a little later. But Euler was not really the first who really posed the problem of bridges of Königsberg. It was Gdańsk or Danzig mathematician Heinrich Kuhn. He's not that well known, he should be. And now we see clearly connection with Königsberg. Euler was never in Königsberg. Even when he traveled from Berlin to Petersburg, he just didn't stop in Danzig or Königsberg. When Kuhn, in fact, was born and educated in Königsberg, and then in 1733 he was offered a job in Danzig, and he worked there he was invited by scientist called Carl Leonard Gottlieb Echlel, who was scientist, correspondent of Leibniz, but was not mathematician. But he recognized talent of Kuhn, invited him to be professor in local high school, Lyceum. So what is the story of bridges of Königsberg? So probably Kuhn brought this puzzle from Königsberg, or at least it was his native town he brought it. Then how Euler learned about problem of bridges of Königsberg? I have conjecture which is very likely how it happened. So in 1734, 1 year after Kuhn came to Gdańsk, there was a war of succession in Poland between Saxonian dynasty supported by Russia and Prussia and Leszczyński supported by France. And Saxonian were winning, but Gdańsk was supporting Leszczyński. So Russian troops surrounded Gdańsk, and finally Gdańsk capitulated, and Gdańsk had to pay a big war penalty to Russia. Even a rich town like Gdańsk was not rich enough to pay such a big sum of money, so they sent a delegation of the important citizens of Danzig, and among them was Echlel. He was a scientist, but he was from distinguished Gdańsk family, so he went to Petersburg. Then they were waiting for a decision of Russia, whether this war reparations will be lowered, and then he was invited to attend the meeting of Petersburg Academy of Science. And at this meeting of Academy of Science, he met Euler. So this is known for sure, but most likely at these meetings he told Euler about problem of bridges of Königsberg. So there's another proof for this, namely when finally Echlel went back to Gdańsk and the reparations were lowered, so it was a successful trip. He started correspondence with Euler. He was really writing for Kuhn, but Kuhn was shy and he didn't write letters, so it was Echlel who was corresponding for him. Anyway, in this letter they talk about bridges of Königsberg as something well known to both of them. There's now no letters discussing the beginning. So, bridges of Königsberg problem, the first really solved problem in Geometria Situs, is coming from Kuhn. Euler solves the problem and make it famous. So now, which name is not yet mentioned, now I think we can go back to our graphs and knots. So I erase names. After this long historical introduction, let's go back to our drawing of knot diagrams. So let's remind you convention, and I got some homework solved by some students and we'll discuss convention. So remember, convention was the following. First of all, for every edge of the graph, so graph has edges and vertices, and I should stress that we draw plane graphs, meaning graphs already drawn on the plane without intersection. And what was our convention? I will use red chalk, even if maybe it's not that well visible, but still it is different than white. So this was our convention. From this convention follows convention for different position of the edge. So let's draw different position. Of course, this is the same convention. And finally, let's rotate vertically. This is when it's vertical, we can rotate even more. Even more. Okay, so we have our crossing for edges in various positions. Now just rotation, one basic case, and then rotate. How to remember this? So I got several answers from you, and I think the best similar to which I am using is the following. We walk along an edge, and then the bridge should be on the left. So once more, follow our rule. I walk along the edge, and on the left is the bridge. And then the rest is tunnel on the right. Okay, so this is our convention. It works here as well. I walk up here, and the bridge is on the left. So this is our convention. Bridge on the left. But you can say, justly so, what if I walk along the edge from the opposite direction? Okay, let's walk from the opposite direction. Still, the bridge is on the left. How it can happen? Of course, we know this phenomena. Everybody, at least in US, is should drive on the right side of the road. Everybody is driving on the right side, and still accidents are rather rare. Because of exactly this, depends on the point of view, but the result is the same. The rule is the same. Everybody is driving on the right, whether you drive north or drive south. So using this rule, I can draw relatively quickly our knots. So let's do some examples, and I got already several homeworks with mostly correct solutions. So first family was family of polygons. So let me erase convention. I will now use the rule bridge on the left. So, polygons. Let's start from the triangle. Then will be square. In the homework I asked to go up to 9. Here I don't have that much space. 1, 2, 3, 4, 5. And maybe let's finish with hexagon. Remember, our notation is polygon n. So this is polygon, maybe a shortly n-gon. So triangle, square, pentagon, hexagon. Let's use our rule. So very quickly, bridge on the left. Bridge on the left. Bridge on the left. So this allows me to draw this quickly. Now we connect, remember the rule was that we connect loose ends of the crossings along edges, or I prefer to call this walls. Wall. This knot has a name, it's called trefoil knot. Trefoil. Or maybe right-handed trefoil, but let's say trefoil. And in Tate table, remember Tate was the first Scottish mathematician, physicist who started tables of knot, because he thought about them as atoms after Lord Kelvin. So this has named 3 crossings, and in fact this is the only up to mirror image. So 3, 1. Now let's go for square. The same, bridge on the left. So I don't have to think much about rotation, bridge on the left. Bridge on the left, bridge on the left. Now we have to connect. One more connection. So this nice diagram corresponding to square. But look at this carefully. How many pieces, so we think about this as 3-dimensional object. How many pieces of the rope we need here? Clearly we need more than 1, because this is here one piece of the rope and here the second. So it has, we say, 2 components. So some people call such object multi-knot, but in standard terminology now we call about this link. So link has many components, and for knot we reserve is only 1 component. So maybe I should say link of here 2 components. 2 components. And here was a knot, and a knot is by definition not a link of 1 component. Still you can find in literature older name multi-link. So it will be multi-link of 2 components, multi-knot of 2 components, but we say link. So we have a knot, 3-1, we have a link of 2 components. What is state notation? Here we say that is the fourth, and he doesn't count trivial knot and trivial link, so it will be the first. And here we put number of components. So if there's nothing put here, it means there's a knot. If you put here, this is 2, and this is link of 2 components. So for exercises and for this to look nicely, I'm not sure we see colors, we draw different components in different colors. So let's say change color of this one. For those of you who will take test, quiz, I will ask draw diagram of links given by plain graph, and then color every component with different color and tell how many components we have. So in particular here, we write that for this link, number of components of the diagram of square, I don't like to draw, so diagram of the square is equal to 2. So this will be proper answer here. Here proper answer will be it is a knot, or if you prefer you can say that number of components is 1. Let's go to pentagon. Again, bridge on the left. 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 Now we have to connect loose endpoints of crossings. If you look carefully at this picture, we see there's really a knot. If you go, it is only 1 component. We did this last time, so this knot has name like trefoil, pentafoil, some people say. And in tables of knot, the atom corresponding to this, it has 5 crossings. And this is the first. And there's a knot. Let's go to 6. So let's go to 6. Let's draw crossings for every edge. Bridge on the left. You can go for here or here. Doesn't matter. And now let's connect them. So this is a knot, a link really, because we see it has 2 components, but we'll check in a moment. Link corresponds to hexagon. But let's check how many components it has. Remember, components is something done in space. So we go. And let's do this. Let's start here with blue. We go with blue. We continue in space, so we have to go under. Remember that on the quiz, when you count components that you change color, you should not destroy crossings. Always you should see which is over and which is under. So I ended. So clearly there is blue component, and clearly we see that red component is similar. Which means that for this not number of components, so I can write by word, I can write com, or I can write link of two components. Oh, it's not visible. Link of two components. Here, blue and red, if you can see colors. So now I will not draw more for the polygon, but let's make some conclusion. We can guess now when you have a knot and when you have link of two components. Knot was for triangle, pentagon. There's no more experimentation, but in homework you see that for 7 and for 9 it was a knot as well. And now link of two components for square and for hexagon, and in homework it was as well 8 edges, and it was link of two components. So let me write here as conclusion. I should erase this, but so I will write this using notation. So number of components, I will write com. Then we take diagram of polygon, n-gon. And our experience was showing that every second is a knot and every second is a link of two components. So this was either a knot, 1, or a link of two components, 2. When number of edges was odd, it was a knot, if n odd, and if even was 2. So this is conclusion from our experimental work. You can justify this kind of easily, that whenever you have edge, we go in, out, in, out, in, out. So if the number of edges is odd, we go twice around before we close. But if the number of edges is even, in, out, after one round we close this. But we don't need such formal proofs, but it's easy to observe. So now let's go to the second family of diagrams related not with PN, not with polygon, but with polygon with double edge. Again, I got several correct solutions. So let's draw this. I will erase our pictures. So Pn was n-gon and Pn prime, n-gon with one edge doubled. And again, let's start from triangle. I will draw this upside down because as usual drawn. So triangle with edge double. Now square with edge double. Now let's say pentagon. I'm trying to make this double edge on the top. Then maybe hexagon. I would like to go to 7. In homework it was up to 9. And finally P7 prime. 1, 2, 3, 4, 5, 6, 7. And let's double So it's prime. This was prime, etc. So the drawing is standard. I will do this, and what I would like you to pay attention is that whether you can get links or always you are getting a knot. Plus you should know which are vertices. Okay, so this we can do pretty quickly. So bridge on the left. Okay. Now connect along walls. And we got the knot we already discussed, figure 8 knot, already considered by listing student of Gauss, and because it's the only knot, it has knot of 4 crossings, so called 4, and this is the first and the only one with 4 crossings. So I said it's called figure 8 knot, I wrote already, but some people, especially in German literature, justly so, call this listing knot. Okay, so let's go here. Do we get knot or a link? Let's do. Bridge on the left, bridge on the left, bridge on the left, and bridge on the left. So this is preparation, and now we connect along edges. Okay. Is it link or a knot? I will not change color because I know it will be a knot, but let's do red, but with distinguished fat line. We go along our diagram. We go along our diagram. Go along our diagram. And you see I finish, which means that it was a knot. This is a knot. It has 5 crossings, and in fact is the first, and is the second, because first was for pentagon. This is the second with 5 crossings, so 5-2. Tate was calling this 5-2 because the knot corresponding to pentagon was 5-1. Let's go next one. Quicker. Bridge on the left. Bridge on the left. Let's connect them. Is it a link or a knot? Again, I can go around. Clearly a knot. Link of one component. And in fact, here it will be the first knot of 6 crossings. So, according to Tate tables, 6, 1. Why not hexagon? As we checked, hexagon is giving a link, and this is a knot. So it's the first knot of 6 crossings. How many of them there are? Well, I commented last time there are only 2 knots of 5 crossings, 5-1 corresponding to pentagon, and 5, 2 corresponding with this square with double edge. With 6 crossing, we have 3 different knots. So this is the first of them. We'll discuss other later. So let's very quickly draw other pictures, just to have them drawn. So these are the crossings. Now we have to connect them. Don't do too quickly because it's easy to make a mistake. Okay, so this is our knot of 6 crossing, not 6, now it is, how many it was, 6, 7. So this is second of 7 because polygon of 7 edges is 1, so this will be called 7, 2. And this is a knot. I will not check this again, go around, and only one thing. And finally, the last one, maybe one observation which allows us to do it quicker. Namely, when you look at our diagrams, always when we go along the knot or along the link, we are going under, over, under, over, under, over. It happens then in this Tate construction from plane graph, always we get alternating diagrams. So this is observation, we will not prove this, but D of G always alternating. This is very important observation, so this will allow me to draw it quicker. Maybe even too quickly, check whether I am not making a mistake. So, first convention, we start from the bridge on the left, but then we know it should be under, then it should be over. Should be under, should be over, should be under, over, under, over. Under, over, under, over. Don't do this initially because it's very easy to make mistake. But this will be our picture. We see the pattern. Here's the clasp, and then we go around like for polygon. So this has how many? 8 crossings, so this will be the first with 8. 8, 1. And it's the first because for polygon we get a link of 2 components. So this is a knot. So notation suggests that it's a knot, but let's still stress. A knot. So just stress once more that in our construction always we get alternating diagrams. Tate initially thought that every link can be drawn using alternating diagrams. Already at the beginning of his basic paper, he wrote that knots are alternating. At the end already he gave 2 counterexamples. It's very funny because he didn't change introduction to his paper. But this will be in the next class. I will show Tate examples and we'll play more. So for the moment we have many examples, we know the rule, and we know that we get always alternating. So the next thing will be homework. Homework will be easy. I will ask you to draw diagrams of 3 kind of well-known plane graphs and count how many components. So let me erase this. So this homework or practice, draw diagram of G for the following G. For the following G and find number of components. Find number of components. we denote this number of components of the diagram of G. To have nice drawing, draw each component in different color. So what are my examples? First will be just square with diagonal. Secondly will be our K4. We know complete graph of 4 vertices. I recall complete graph of n vertices is graph with n vertices, and every pair of different vertices is connected exactly once. That is the K4 drawing. And one more will be 2 boxes like this. So draw for each of them, find number of this, and send me answer if you are my student. And otherwise practice. If you like to be more theoretical, prove that such diagrams are always alternating over, under, over, under. Thank you.